Welcome back to the Crystal Clear Electronics 2 video series. We have reached the 8th chapter of the curriculum. The topic of this one is serial communication, but before we start, I would like to introduce our presenter today, Szabolcs Pályár, who teaches mathematics and physics at the ELTE Bolyai János Practice High School in Szombathely. Szabolcs, could you please tell us a few words about you, in case someone doesn't know you from the Crystal Clear Electronics 1 video series?
Hello! Electricity is my favorite area of physics, so I'm excited to have been organizing crystal clear electronics study groups for high school students for 5 years. This year, for the 4th time, my students and I participated in the accompanying summer camp at Lake Balaton. At these camps, we have the opportunity to work even more intensively on the curriculum. Dani, please introduce yourself as well.
I am Daniel Szabó, a third-year electrical engineering student at the Budapest University of Technology. During my studies, I have learned the fundamentals of electronics and informatics, and now I would like to share some of this knowledge. The 8th chapter was written by Béla Szabó and proofread by Szabolcs Hadarics. This chapter will cover serial communication with a focus on the I2C communication protocol. In addition to this, there are a number of different standards. For example, in chapter 10, we will also take a closer look at the use of UART, USART, CAN and USB. Here are all these abbreviations, or acronyms in other words. They seem to have exactly the same purpose, to allow our embedded devices to communicate with each other. We have to learn them all to be able to build any kind of electronics. After the first try and some practice, you will understand that each mode of communication has its features, and therefore each will be ideal in a different environment. This chapter will be divided into 3 videos. In today's video, we will discuss how 2 devices can share data. In the next episode, we will learn how the I2C protocol works, and in the following episode, we will test what we have learned so far with an example of a luminance meter. Szabolcs, how would you describe machine communication to a non-expert person?
To start with, think about how we communicate with people in real life. Here too, there are unspoken rules, such as we don't cut each other off, or if we ask a question, we wait for the other person to answer. In the world of electronics, these rules are much more precise, so we need to be aware of them when designing communication lines. Just as important is the direction in which we want to transmit data. These can be simplex, half-duplex, and full-duplex. In simplex transmission, data can only go in one direction. So we are talking about a network where the transmitter and receiver roles are constant. In half-duplex communication, the transmitter and receiver directions may change at the end of a communication cycle, so our data stream can be bidirectional. It is important to note that at any point in the time, the data flow is only in one direction. During full duplex data transmission, both sides in the communication can send data to the other simultaneously.
Szabolcs, it's all clear. I think we can sit at the table so that we can examine the issue more easily.
Let's go!
Even a beginner embedded electronics developer should be aware of what is meant by the serial communication line and the parallel communication line. Can you elaborate on this topic?
Yes, let's compare them with the following simple example. Suppose you want to transmit 1 byte or 8 bits of information using simplex communication. In serial communication, the bits of our data pass sequentially between our 2 devices, whereas in parallel communication, we are able to send and read several bits at a time on the other side. Serial communication therefore takes more time, and parallel communication takes more communication legs. But unfortunately, as we already know, things are not that simple. Plus, costs can occur. We'll show you some of them for I2C. These 2 types of communication can easily be related to everyday life. For example, serial communication is similar to when we used to tap out Morse code on our school desks as children. In this case, short or long sounds were made one after another. On the other hand, a great analogy for parallel communication is braille, where each character is identified by a 6-dot rectangle. Here, the brain processes 6 bits of data simultaneously to decode the letter. However, let's return to our previous figure, as there are still some useful details to discuss. Looking at the first picture more closely, we can see that we have a signal at a higher voltage level for some time, and then at a lower voltage level. The higher level will represent logic 1, while the lower level will represent logic 0. From these two states, we can see that this is a two-state, in other words binary data stream. Each bit is the same width, so they last for the same time. Let's count the data bits. You've probably learned from previous chapters that in embedded programming, we start counting from 0. The least and most significant bits have their own names. We usually just refer to them by their abbreviations. These are the LSB and MSB. So in our example, the 0 bit will be the LSB and the 7th will be the MSB. Based on the information just given, please try to decipher what value you see in the picture. Feel free to pause the video, and when you are done, you can check your result. To find a solution, you need to decide the value of the bits one by one, and then look at the local values starting from the MSB and moving towards the LSB. So in the hexadecimal numeral system, the result is 0xAD. As in embedded systems, we are now mainly focusing on how to attach simple peripherals to our microcontrollers, and in such cases, we relatively rarely use parallel communication protocols. Therefore, we will not look at such examples in the rest of this chapter.
We have this very cool black electronics, which is also in the written curriculum. I suggest we now take a look at the communication devices on it, but mostly just the I2C ones, because we'll be dealing with them in the upcoming video. On this board, you will find an STM32F405 microcontroller with various sensors on the top and a couple of connectors, including one to connect the display to the I2C bus created on the panel. Of these sensors, the ones of interest to us at the moment are the light sensor, the thermometer and the humidity sensor, as these 4 devices are on the printed circuit board, PCB, with the controller on the I2C lines. Of these, only the microcontroller can initiate communication, the others have to carry out the instructions given to them. Such instructions include, for example, that a sensor should give its measured value, or that the display should show it in the way we have specified.
I'd like to draw the viewer's attention to the fact that in this chapter, we will use a light sensor as an example to connect to our microcontroller. However, the aim is not to teach the viewer how to connect this light sensor to this microcontroller, but to enable you to connect any device communicating on I2C to any microcontroller. Therefore, we encourage everyone to get a cheap I2C IC, even for a completely different purpose, open its datasheet, and integrate it into the system.
Thank you, Szabolcs, for this brief introduction. This is all we had time for, but don't worry, we're not going anywhere. In the next video, we will explore the details of the I2C protocol together. See you all!
See you!